This is Science Max, Experiments at Large. Science Max! This episode of Science Max is a messy one. We're looking at solids, liquids, and gases, and things in between, like cornstarch mud. Today on Science Max, Experiments at Large. Behold the power of states of matter! Greetings, Science Maximites! I'm Phil McCordick. I think I overdid it with the fog machine. This is Science Max, Experiments at Large. Can you even see me? Let's go over here. Today we're talking about states of matter. Now there are three main states of matter. Solid, like this table, liquid, like the water in this beaker, and gas. Yes, thank you. And we're also going to be looking at the things that kind of go in between. Things that are sometimes solid, sometimes liquid, like cornstarch mud, which is very easy to make. All you need is water and cornstarch, which you can get at the grocery store. Mix it up however much you want. Just remember, 2 parts cornstarch to 1 part water. Twice as much of this than you have of that. Very easy. Mix it up and you get cornstarch mud, which sort of seems like a liquid unless you hit it. And then it becomes solid. But if I pour it, it's a liquid. Even if I hold it in my hand and I hit it really fast, it turns into a ball, and it will stay in a ball as long as I keep hitting it or squeezing it. But soon as I stop, it turns into a liquid again. Now we're gonna max this out. We'll go through the portal and learn more about solids, liquids, and gases. Yeah, right. That's why I'm going to the Center for Skills Development and Training. Oh, no, wait, that's the code for the fog machine. Wait, stop. Stop, it seems to be stuck. Oh, never mind. I'll fix it later. Right. Hey, Judy, how are you?
Hi, Phil, how are you?
Good. Judy is going for her PhD in chemistry, right?
Yes.
Fantastic, because that means you can explain cornstarch mud to me. Now, is this a solid or is it a liquid?
Well, it kind of has properties of both. It's called a non-Newtonian fluid, so that makes it a liquid.
A liquid? Well, I mean, it pours like a liquid, but when you hit it, it's a solid. So why does it turn solid when you hit it?
So when you're pouring it, the particles are still far apart, so they can't interact with each other, and so they stay a liquid. But when you're hitting it, you're jamming the particles together, and they line up to become a solid.
Now, does it still work the same way if we have a lot more of it?
It should.
Great, because I've got this 20-kilogram bag of cornstarch, and I have 34 more of them.
Wow, that's a lot. But I think you'll need a much bigger container.
Much bigger container, great. I got some wood over there. Why don't you go, and I'll follow you.
All right.
I'll follow you. I'm coming. Yeah, thanks, Ramona. And give me one of them fizzy drinks. Not too fizzy, just sort of medium fizzy. Thanks a lot. Hello, do you have trouble knowing what is a solid, liquid, or gas? Are you confused by Jell-O? I mean, which is it? Is it a solid or is it a liquid? Water is a liquid, but what about when it's ice? Well, you gotta know your states of matter. There are 3 main states of matter: solid, liquid, and gas. And there are 3 rules that you need to figure out which one of them is which. Does it flow? Does it fit the shape of its container? And can you squeeze it? Rule number 1, does it flow? Solid, liquid, gas. Here's a gas. Does it flow? Do the particles pour over each other and cascade down? Yeah, they do. Does a liquid flow? Yeah, it does. Does a solid? Nope. Rule number 2, what happens when you put it in a container? Does it take the shape of the container? Gases take the shape of the container. Liquids takes the shape of the container. Solids do not take the shape of their container.
know what you're thinking. You're thinking, I get the whole pouring and taking the shape of the container, but come on. Liquids and gases, they do both of those things. Well, it all comes down to rule number 3. Can you squeeze it? Now, solids, you can't really squeeze them. Liquids, you can't really squeeze them. Gases, ha-ha, bam, you can squeeze them. You see, gases compress. Liquids and solids, they don't really compress very well. The other difference between gases and liquids is gases will take the shape and the volume of the container they're put in. Liquids don't do that. So there you go. Solid, liquid, gas. And the rules. Does it flow? Does it take the shape of the container? And can you squeeze it? Now you know your states of matter. That'll be $6.50. Cash only.
So what is cornstarch mud and how does it work? Well, cornstarch mud is a non-Newtonian fluid, which means it behaves differently than you, or Newton, would expect. Here's cornstarch, and here's water. Cornstarch is made up of large, blocky molecules like this. Water is made up of much smaller, rounder molecules like this. When you put them together, it looks something like this. It all has to do with how the molecules slide past each other. When you put light pressure or slow pressure on the mud, the water molecules and cornstarch molecules have time to shift out of the way. But when you put a sudden pressure on it, the water molecules squirt out of the way, but the cornstarch molecules don't have enough time. So you get a section that's nearly all cornstarch, which acts as a solid. Cornstarch mud is a shear thickening fluid. Shear is talking about the force of things sliding around, in this case, the molecules. So when the shear force is strong, the fluid thickens, shear thickening. So here's the plan. If Judy and I make enough cornstarch mud, could we run across it? Let's find out.
Yeah, I think mine is just the right consistency. How's yours, Judy?
I think I'm ready too. This is much harder than I thought.
Yeah, it's really hard to get it mixed at the very beginning, but
Yeah.
mine is ready to go. Okay, here we go. First
good.
batch. You ready?
Yep.
Dump it in. Woo! Woo! I thought that would be more.
I thought so too.
It's really not filling this up very much, is it?
No.
Huh, that's a lot of cornstarch. This is great, but I think we're gonna have to go a little faster than this.
I think we need some sort of mixing device.
Yeah, I mean, we don't have to do this by hand. We can get some sort of machine to help us.
Yeah.
Right on, high five.
Oh,
We shouldn't high five when we have this stuff on our hands.
Nope.
Yeah, good call. This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar. You can use brown or white. I like to use brown. And an adult. Here's why you need an adult. You want to dissolve 3 cups of sugar into every cup of water. And you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container. And then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how can we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big would definitely not be good for my teeth, so yeah.
So our big experiment is to take a whole lot of cornstarch and fill a trough to see if we can run on it. But mixing it by hand was going to take forever. So Judy and I got a drill with a mixing attachment on the end.
Whoa, sorry. All right, so Judy, I'm noticing a bit of a problem here.
What is it?
Well, if I mix at the top, everything's fine. But as soon as I get it a little bit deeper, and then it gets really tough, and the whole bucket starts to spin, and the drill stops.
Yeah, I think it's because the drill's trying to mix it too fast. When we're mixing it by hand, it's slow and you can still let it stay a liquid, but now you're just making it a solid.
Right, because it's a sheer thickening fluid.
Exactly.
So if you hit it really quickly with something, like the blades of this spinning really quickly in the thing, it'll suddenly turn into a solid, and it'll be really hard to mix.
Yep.
So we go slow. Going slow. Going slow. Suddenly realizing that if we go slow, we'll be here forever.
Yep.
You know what I think we need? Whoa, sorry. You know what I think we need? We need a different way to mix this.
Yep.
We need a way to mix more of it, and we need a way that it doesn't hit it with blades that suddenly go through it really quickly.
Something that can mix on a large scale, but slowly.
I have just the thing. Come with me.
All right.
The interesting thing about bubbles is they're a gas surrounded by a liquid. So get some dish soap and some water, and then be Science Maximites and find things around the house that you can make bubbles out of. Just about anything that has holes will do. Or I like this one. I call it the loud bubble. Or now it's time to max it out. I'm here at the Ontario Science Centre, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in
Okay,
there,
right
right in
in.
there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close.
great.
Did you see that one? You give it a shot. Nice! Oh, check that out! That was amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Maxed out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment. But it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff up.
Come on back. Good. Little bit more. Perfect. A cement truck is a perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it, and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo. Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine. This is liquid nitrogen. Nitrogen makes up most of the air we breathe, but if you get it really, really cold, it turns into a liquid. The fun thing is you can use it to make other things really, really cold too, like this banana. I have frozen this banana solid thanks to the liquid nitrogen, and normally a mushy banana would not be able to hammer in a nail, but whoa, because it's frozen, I can hammer this nail into this block of wood. So that got me wondering, if I can turn a banana into a hammer using liquid nitrogen, could I turn a pumpkin into a sledgehammer? Let's find out. Pumpkin sledgehammer, take one. No, I think the answer is no. You cannot turn a pumpkin into a sledgehammer with liquid nitrogen. All you can do is make a really, really big mess. I'm gonna have to clean this up, aren't I?
Now we have a cement truck to help us do the mixing for our cornstarch mud. After making a giant mess getting the cornstarch into the cement truck, it's time to see if it worked.
Hey, Phil, how's it going?
Yeah, it looks like it's mixing pretty well. I'm really glad we're not doing this by hand, because it'd take a really long time. We've almost got it at the right consistency, but it's taken some time. But it's getting a little dark out, Judy. I don't know, do you want to quit and go home?
No.
Of course not. That's not what we do in science. Oh, here we go. Yeah!
Awesome.
All right, let's see it. Let's see if it's... I like how it comes down in little steps. And look, it's working just like it should. I hit it, and it's solid, but you can see it's pouring like a liquid. Yeah, here comes a big wave.
Wow.
Here it comes. Oh!
And it's totally filling up.
Oh yeah, filling up really fast. I think we should stop pouring very soon.
Yep, we may not have a big enough trough. Yep,
Liking it.
it's good.
Yeah. I think it's time. It's not even done pouring, but I'm gonna try it. Okay, you ready? Whoa.
Oh, and you did it!
Whoa. You can't. You have to get back onto the sides before you stop moving.
Or else it becomes a liquid.
All right, it's your turn.
Okay.
Here.
Go.
Okay, ready?
Okay.
You gotta hit your feet really fast.
All right.
Here, go. Yeah!
This actually works.
Because cornstarch mud is a sheer thickening fluid, it means it stays a liquid until you hit it suddenly, like with your hands, or in this case, our feet. And then it turns to a solid. So as long as Judy and I keep slapping our feet down with enough force, we can walk on top of it.
One more dance.
All right.
And
let's
tell you
do
what,
it.
we'll do one more dance.
All right, let's do that.
Okay, ready?
All right.
And go. All right.
All right.
There you go.
We've done it.
Solids, liquid, gases. Thanks very much for joining us on Science Max Experiments at Large. Woo!
Science Max! Today on Science Max, we're looking at chemicals. Chemicals make up everything around us, and we're finding out which ones you can mix together to make spectacular science.
Whoa! Woo! Cutest science ever.
Today on Science Max Experiments at Large.
Greetings, Science Maximites! My name is Phil McCordick, and the name of the show is Science Max Experiments at Large. Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you, The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be Science Maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. And that's what we're gonna be looking at today, chemistry in all its forms. And of course, because it is Science Max Experiments at Large, we're going to max out the vinegar and baking soda volcano. So I'm off to the Center for Skills Development and Training. Come on. Hey, Talina.
Hi, Phil.
How you doing?
Good, how are you?
Good. This is Talina. She's going for her PhD in chemistry from McMaster, right?
Yep.
Awesome, which means you can help me max out the baking soda and vinegar. We need vinegar. You grab that vinegar. And vinegar volcano. So what happens when we mix these two chemicals?
Well, vinegar is an acid and baking soda is a base, and when you mix them, they neutralize each other to produce carbon dioxide and water as a byproduct.
So acids and bases are kind of like opposites.
Yep.
So I guess that makes sense. When you put them together, crazy stuff happens.
Yeah.
Awesome, chemistry. Okay, so I wanna use this much vinegar and this much baking soda.
What's with the fish tank?
The fish tank is where I wanna mix it all together. What do you think?
Awesome.
Maxed out. Okay, let's move the fish tank somewhere where we won't make a huge mess. It's a little heavy with all that. No, we're gonna have to take a couple trips. That's kind of heavy. Okay, so we'll take this and that, and then this, and that. No, hold on. I can do it. Just one more. Okay, good. Okay, good. Yeah. I took too much. Uh-oh. That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes. But if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on, made of chemicals. My lunch, chemicals. Roller skate, chemicals. My jacket, chemicals. This guitar, chemicals. My shoe, chemicals. This watch, chemicals. This fish, chemicals. Chemicals. Me, chemicals. You, chemicals. Ramona, chemicals. No, I said your chemicals. Never mind. This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter. Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got 1 oxygen, 2 hydrogen, bam, you got a water molecule. 1 carbon, 2 oxygen, hey, it's carbon dioxide. 2 carbon, 2 oxygen, 4 hydrogen, skadoosh, vinegar. 1 sodium, 1 chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar.
Let's take a closer look at what's going on when we mix vinegar and baking soda. All chemicals are made of atoms. There's only 4 types in our reaction: carbon, oxygen, hydrogen, and sodium. When they go together like this is a molecule of vinegar, or acetic acid. And this is a molecule of baking soda, or sodium bicarbonate. When chemicals react, they switch atoms. That one goes there, this one goes over here, and then this one turns into this, and then what you end up with are new molecules. This one is called sodium acetate, and this one is carbon dioxide gas, the gas you breathe out. And do you recognize this one? Right, water, H2O. Why all this happens gets complicated, but the study of chemistry is all about how molecules are built and react with other molecules.
All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our 3rd bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh, yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid. The rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it.
Our vinegar and baking soda reaction went pretty well. But now we're gonna try it with a much stronger type of the same kind of acid you find in vinegar.
Carefully putting this down. And watch out for the baking soda. You never know when it'll get out. And, well, I guess that's just baking soda, huh?
Yeah, that's pretty safe.
Yeah, okay, good. So this is baking soda vinegar volcano version 2. We have this differently shaped glass. What do you call this again?
That's an Erlenmeyer flask.
Why is it called that?
It's actually named after a scientist.
Did he look like that? Was he sort of shaped like this?
No.
No? Was he just a good chemist?
Good scientist, and I think he designed the glass.
Oh, see, there you go. So if you want to have a glass named after you, be a good chemist and design a glass. I want to make a fill beaker. So this is 100% acetic acid.
Yep.
And what's the difference between this and vinegar?
Vinegar has 5% of this and 95% water. But this is 100%, so it's much stronger.
Much stronger. Can you put this on your French fries?
No, I wouldn't be putting it on your French fries.
No? As chemicals go, how dangerous is this?
It's not too dangerous, but you definitely don't want to be breathing it in, and you don't want to be eating it.
Or getting it on your skin. That's why I'm wearing these fancy gloves. So what I'm gonna do is I'm gonna pour the acetic acid in this. What's this called?
That is a graduated cylinder.
Because it finished school. So it graduated. Now you're gonna mix water and food coloring and soap all together.
Yep.
And pour it into there?
It'll help dissolve some of the baking soda, so hopefully it'll react better with the acid.
Sounds good. Face protection.
Oh.
All right, that's good. And now, when we do it, I want to add the funnel at the end to like accentuate the concentration of, but I don't know if it's gonna go so fast that I won't be able to get it in there, but we'll try it.
Try it.
Vinegar baking soda volcano version 2. Woo!
Good thing you got the mask.
It smells a lot like vinegar. It's really strong.
Oh.
That was pretty good. But what can we do to make it even bigger?
Well, you could try using a different chemical reaction.
Ooh, okay. Like what?
The decomposition of hydrogen peroxide produces oxygen gas, and so that one's pretty vigorous if you use a catalyst.
So we want something that makes a lot of gas so that it makes a lot of bubbles when you put the soap in it.
Yep.
Great, let's do it. And the sooner we leave that smell, the better, I think, for my taste. Today we're combining two different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. Very cool and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous. So,
So, what happens if we combine these two deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land? No, we create salt. Good old normal table salt. These two substances combine to make NaCl, salt. Something completely and totally safe. Chemistry.
We've gone from vinegar and baking soda to 100% acetic acid in baking soda, and now we're doing the
Vinegar and baking soda volcano version 3. No longer vinegar and baking soda.
Nope.
What are we using this time?
So here we have some hydrogen peroxide.
Oh, that's the stuff you use at home to put on a cut, right?
Yeah, but the stuff at home is only 3%. This one's 30.
So much stronger,
Much-
10 times stronger.
Yes.
And is this more dangerous?
It's definitely corrosive, so wear your gloves.
Corrosive means it could eat your skin,
It can burn your skin a little
which
bit.
is why we are wearing gloves and blast shields. What's gonna mix with this?
So here we have some potassium iodide, which is a salt, and it's mixed in with some water.
The most important part of this reaction is the fact that it creates gas.
Oxygen
which
gas?
makes bubbles when you put in dish soap, right?
Yep.
So one big squirt of dish soap like that. Mix it up. Now we go over to the blast zone.
That's plenty.
All right. Now that's a reaction. Looks like there's steam coming off here. Why is that happening?
Well, it is an exothermic reaction, so heat is being generated as the reaction proceeds.
Oh, cool. Can we lift our visors now?
Yep.
Awesome. And what's being released? What's the gas that's coming off here?
So it's oxygen gas that's being produced.
Oxygen. What we want to do is make this even bigger, but first, can we do it again?
Sure.
Because I have an idea. Hold on. I think we should repurpose our old volcano. What do you think?
Sounds like a good idea.
Okay, so if we put it over here. All right, volcano version 3.5. Hydrogen peroxide, potassium iodide. Right, here we go. Whoa!
Looks like lava.
Whoa! Look at that. Now that is a big volcano eruption.
Just covered the town.
That is completely, yes. That town is gonna be very clean because it's all soap bubbles. It's the cleanest volcano this side of Science Maxville. So I still think we can do this bigger, though, right?
I agree.
Oh, I know. What if we use some sort of a tube, like maybe one of these, right? And then we attach it to like an air compressor.
I think you'd get some height.
Yeah, and we go outside.
The atom in 60 seconds.
The atom is the smallest unit in a chemical element. Atoms are made of 3 parts. Part number 1 are these guys, protons. They have a positive charge. The number of protons determines the element. 1 is hydrogen, 2 is helium, 3 is lithium, and so on. The protons sit in the middle here, which is called the nucleus. They sit in here with part number 2, these guys. They're neutrons and they have a neutral charge. Now I've got 8 protons and 8 neutrons in this nucleus, making this an atom of oxygen. Orbiting around the nucleus are these tiny guys. They're electrons and they have a negative charge. I will demonstrate using kittens.
Kittens are perfect because just like electrons, kittens are really small. And just like electrons, kittens move around randomly. You never know where they're going to be, but an oxygen atom should have 8 kittens, or electrons, somewhere inside. These kittens are constantly escaping, but guess what? That happens with electrons too.
There you go, the atom, a nucleus of protons and neutrons surrounded by randomly moving electrons. Cutest science ever. How do you guys feel? Did you learn something? Huh? Pause up. Who learned something?
Talina and I have made a bunch of chemical reactions, but in our quest to max things out, we've got a new plan. Hydrogen peroxide and potassium iodide create gas. One way to max out the reaction is to contain the gas in something like a tube. We're gonna put the hydrogen peroxide in the tube first. Then we're gonna put in the potassium iodide in the top through a one-way valve. Then we're gonna pressurize the container. When it finally reacts, it will shoot up through the valve and we'll see how high we can get our stream of bubbles to go. But be warned, tapping anything and not letting it escape is never a good idea. So we've got a release valve to make sure things work out. This is one of those experiments that's definitely on the list of don't try this at home.
Vinegar baking soda volcano version 4, hydrogen peroxide, potassium iodide. And what we're gonna do this time is we're gonna put it in this tube. Hydrogen peroxide goes in here. And we've got, Talina, do you have the potassium iodide in syringes?
Yeah, 2 syringes full.
2 syringes full. About there is good. And then soap. Good amount of soap in there. And so what we're gonna do is we're gonna close this off and tighten it up. And then we're gonna pressurize the whole system. And then we're gonna add the potassium iodide. And it's going to be spectacular, we hope. Okay, that's on tight. This is all good. Putting this down here. And potassium iodide goes in here.
Ready?
Puts down. Ready? 1, 2, 3, go. And we back away slowly. Whoa! Whoa!
Yeah, that's what I'm talking about. Okay, let's check it out.
Woo! All right, there you go. Vinegar and baking soda volcano maxed out. Thank you, Talina. That was great. If you guys want any instructions for the stuff that we've done today, they're all on the website. And thank you very much for watching Science Max Experiments at Large. We kind of need to clean up a lot, don't we?
Yeah.
We have out here, we have the other room. So tell you what, you get a mop, I will get the hose and a wheelbarrow for the suds.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult.
Science Max!
Taking something flimsy and making something strong.
Whoa, pasta bridge!
We build things out of pasta, sand, and paper to show how you can use science to make something strong out of something weak.
Dry sand, wet sand, science sand.
It's all how you build it. Today on Science Max, experiments at large.
Oh, hi, Science Maximites. Have you ever been eating pasta and wondered, what could I build with this? Could I build something that could hold an impressive amount of weight? Well, I have, and that's what we're gonna do today on Science Max Experiments at Large. But we're not gonna use cooked pasta because it's too delicious. We're gonna use uncooked pasta, which is less delicious, but it's great for building. We're gonna make a pasta bridge. Here's how you do it. First, you wanna start with a plan. And then you want to take your pasta, I'm saying pasta, but of course spaghetti is usually the best thing to use, and lay it out on your plan. The reason you have a plan is so that you can make sure all of the spaghetti is exactly the right length. Lay it out on your plan, perfectly aligned like that. There. And now it's time to glue it all together. Now you can use white glue, but it takes a long time. So I suggest a hot glue gun, but make sure you get an adult's permission before you use one of these, okay? So you take your plan, you lay it out, you glue it up. Don't glue it on the paper because that will be bad. And you will end up with your truss, and it looks just like this. Now remember, you want 2 sides because those are the sides of your bridge. And as you can see, I've used several strands of pasta because that'll make it a little bit stronger. Once you have your trusses, it's time for the next part of the plan. This is the roadway, and it works the same way. Lay out your pasta, glue it up, and bam, there it is. Now, you put your trusses on your roadway, and you glue them all together, and you also want to put some struts along the top here, probably, to keep it nice and rigid. In the end, you will end up with a fantastic looking pasta bridge. Pretty good, huh? pasta bridge. No other bridge could claim to be 100% pasta. Minus the glue, 99.8% pasta, 0.2% glue.
I say there, Captain. Set sail. Set sail for the land of pasta bridges.
Now, if that was pretty fast for you, don't worry, all the instructions are gonna be on our website. Now, a bridge isn't a bridge unless it spans a gap, because that's what bridges are for. So you put your pasta bridge up there across the books like that, and then you can see just how much weight the bridge holds. It's pretty impressive. If you build it right, even something as flimsy and as delicate as pasta can hold quite a bit of weight. I like to use big, heavy blocks and put them in the middle where there is no support from the books whatsoever, and just keep adding heavy things and see how much weight the bridge will hold before it breaks. How much will it hold? Well, I'm not gonna tell you. That's where you get to be Science Maximites and find out for yourselves. And now, we're gonna max it out. Today on, oh, my pasta. Today on Science Max Experiments at Large, we're gonna be looking at how fragile things can become strong if you build them right. We're also gonna be maxing out the pasta bridge experiment to see if we can make one that's strong enough to hold me. You think we can do it? I know I have no idea, but I'm going to the Center for Skills Development and Training to find out. Oh, hey, Kyle.
Phil.
How you doing?
Great, thanks.
Awesome. This is Kyle. He's got a master's in civil engineering. Did you want some pasta?
I'm good.
I can go back and get some more.
Really, I'm good.
Okay. So what does a civil engineer do?
Well, a civil engineer builds the world around us. Talk about our homes, keeping us warm in the winter, our roads, hey, even our bridges.
Bridges, that's fantastic, because that's what I need your help with. I want to max out the pasta bridge.
Awesome.
I want to make one big enough that I can walk across it.
Okay, that's never been done before.
I know, right? You think we can do it?
We're gonna need a lot of help to do that.
We don't need help. All we need is a lot of pasta, which I have. Ha-ha!
Nice.
What do you say?
Yeah, let's give it a shot.
Okay, we'll give it a shot. Why don't we just take some to start, and then...
In order to max out our pasta bridge, the idea is to take many, many strands of pasta and just keep gluing them together so the long beams of pasta in our giant bridge is nothing but many, many regular-sized strands of pasta. Here's where we were after 20 minutes of gluing.
There, that's nice.
Yeah, I think this piece is done.
Okay, so how does it work? Is it strung? Whoa.
Well, let's give it a go, eh? Yeah, I think this will hold.
Great! So we just need to build a few more of these then, right?
Yeah, that's right.
How many more?
212 more.
212 of these.
More.
212, but it took us like 20 minutes to make this one.
Yeah.
Oh, well, I guess so. I mean, this is Science Max Experiments at Large. That's what we do. We just keep building, and, you know, I don't have any plans for the next while, so we can...
Phil.
Yep.
I think that there's a better way of doing this.
I would be delighted to know there's a better way. It'd be faster than this.
Much faster.
Sure, let's do it.
Awesome.
I'm just gonna put the pasta back in the bag because it'll
Phil,
get stale.
You don't have to do that.
No, but it'll get stale.
Phil, I'm gonna call in one of my friends. We're probably gonna need some more help with this.
Oh man, that's a great idea. Sorry, that's a great idea because
Yeah.
Because at least we could get your friend to help clean up.
Better sandcastles in 80 seconds.
Building sandcastles is fun, but you can't use dry sand because it doesn't stay up very well. You have to use wet sand. But even if you use wet sand, it doesn't hold a lot of weight. But if you use sand with the power of science, it does hold the weight. Dry sand, wet sand, science sand. Here's what's going on. Say these ping pong balls are grains of sand. When they're dry, they don't hold together very well. That's why you can't build a sandcastle out of dry sand. But if you get the sand wet a little bit, the grains of sand will hold together a little better because of the surface tension of the water. That's why it's easier to build a sandcastle with wet sand, but they still won't hold much weight. But if you add something that creates even more friction between the grains of sand, like say this sandpaper, it will hold the weight. So here's what you do. Take window screen and cut it into circles. Make sure you get an adult's permission first, okay? Deal? Put in a layer of sand, pack it down, and put in a circle of window screen. And a layer of sand, pack it down, circle of window screen. Then, you guessed it, layer of sand, pack it down, circle of window screen. The window screens are gonna add more friction between the grains of sand and will make your sand castle strong. Strong with the power of science. And then you can put lots of weight on it. And there you go. Sand with the power of science. Okay, I had to max it out. Let's see how strong science sand really is. Huh? Science!
Our pasta bridge was going to take a long time to build out of individual pieces. So we have a new plan.
Hey, Michaela.
Hey, Phil.
How you doing?
I'm great. How are you?
Good. This is Michaela. She's an undergrad in industrial engineering, right?
I am.
And you and Kyle have a new plan for how we can build our pasta bridge that's not gonna look like this.
Oh, man.
This is the best that Kyle and I could do with 20 minutes.
Okay, well, I have better.
Good, I'm glad. How are we gonna do it?
So instead of that, we're gonna try something like this.
Oh, okay. This is sort of like a giant burrito kind of thing, right?
Yep,
But we're going to build the bridge out of this.
exactly.
We're gonna make it longer though?
Yep, we're gonna make it 8 feet long. We have this long pole, right?
Yep.
And we have sheets of this pasta. We're gonna put them on the diagonal,
Okay.
and we're gonna roll it, but we're gonna start from this corner, and we're gonna keep rolling.
And don't
All
forget
right?
to add water.
And we gotta add water.
I'll add the
'cause-
water.
Okay.
Adding water, just like this?
Yep. It helps the pasta to stick together. So as we're rolling, we're rolling, we're rolling. We're gonna keep doing this with a bunch more sheets so that it gets really, really long, like 8 feet long. And when we're finally done rolling, we gotta spray it with some varnish,
Yep.
and so it all holds together.
Great, and then it's gonna be about this thick
Yeah,
when we're finished with it.
exactly.
This is going to be one of the parts of the deck of our bridge.
Great, so each one of these large pieces is gonna be like one single strand of pasta and the little bridge with it.
Yeah,
We need a lot of these.
a lot.
A lot.
Yeah.
Still, it's a lot faster than doing it piece by piece with just the spaghetti.
Oh.
Every time I hold it up, you make that noise.
Oh. Oh. Oh.
Awesome. The shape of something makes a big difference in how strong it is. Get some toilet paper rolls and put them in a square, and then stack books on top of them. They can hold weight. Thing is, they can actually hold a lot more weight than you probably think. In fact, the amount of weight just paper in a tube can hold is really kind of impressive. Ha ha! And now, let's max it out. Bill's weight on 2 toilet paper rolls. Nope. Bill's weight on 4 toilet paper rolls. Nope. Bill's weight on 6 toilet paper rolls. Nope. Bill's weight on 10 toilet paper rolls. Ha! Ha ha! Phil's weight can be supported by 10 toilet paper rolls. But what if Phil jumps? Ha 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 ha. Didn't really work.
Kyle and Michaela's plan is to use a long pole and sheets of uncooked pasta. We roll the pasta around the pole and spray it with a little varnish. We roll sheets and sheets of pasta along an 8-foot-long pole, making many layers of pasta. Then we wait for it to dry and remove the pole. What we have is an 8-foot-long hollow tube of pasta that becomes a single piece of the bridge. Then we attach a bunch of these pieces together and use more sheets of pasta to glue them into the shape we used for our small pasta bridge.
We're making our giant pasta bridge by wrapping sheets of pasta around and around the poles using the technique we just had, making a whole large pole out of many, many, many sheets of pasta rolled around each other. And we've made a giant truss. Look at this. This is great, guys.
It's looking pretty good.
Yeah. If I hit it, you think it'd stay together?
No, stop.
What?
This is pasta, not steel. It's only made to just hold you.
Kyle, what do you think are the chances that this is gonna hold me when we build it?
Something like 50-50?
Not bad. Michaela, what do you think?
I'm gonna hope for the best.
Hoping for the best. That's exactly the kind of gray area we like to work in at Science Max Experiments at Large. Experiments at Large, I don't know if anybody's even ever done this before.
Not to my knowledge.
I don't think so.
Which is why we have no idea if it's going to work. Okay, so one more of these, because these are the sides.
Yep.
Roadway, and then the top.
Yep.
All right, let's do it.
While we're waiting, it's a good moment to point out one of the things that makes our bridge really strong. That is triangles. As you can see, the truss, or the side of our bridge, is really just 3 big triangles. Triangles are very strong shapes to build with, and they work great in bridges. Now it's time for Science So Simple, a caveman could do it. This is a caveman. Today we are going to teach this caveman how to build a strong structure. Here are some boxes. Go on and build a shelter, and I'll come back and see how it worked out. No, that's not right. You need to build walls by stacking boxes on top of each other. That's how you build. Understand?
Oh, yeah.
I'll come back later and see how it worked out.
Yeah.
Uh-oh. Does that look right to you?
Yeah.
Look at those boxes. They're stacked on top of each other. But if they are in tall stacks, what would happen if you push on the wall? You see? Walls don't stay up if you build like that. Let's try again. I'll help you this time. First, lay out the foundation, where your wall should go. Good. Now let's make the second level. No, don't put it right on top. You need to stack in between. That's how you make a strong wall. Okay, I'll come back later. Nice work. Why don't you give it a try? Looks strong, but you forgot a box. Join us next time when we talk about how to make a door.
Building a door in a wall is hard, because how do you make a big gaping hole in your wall without your wall falling over? Well, people have come up with lots of ways to put doors and windows in walls made of stone blocks over the centuries. And you can do this at home with books like I'm doing, or with building blocks. Just go up until you're happy with the height, and then stack each next layer a little closer to the middle until the final layer touches just like this, And then you take a big heavy book and you drop it right on top. And it's pretty stable. And you've just made a doorway. It works even better if it's part of a wall because you want extra weight on the outside of these books here. So of course, I had to build one that was part of a whole wall. This is the same Corbold arch built out of little building blocks. And as you can see, I went closer and closer together until it meets at the top, and it is very strong. Whoa. Ha-ha! Now, let's max it out.
The kind of arch we're building is a Corbold arch. And the Science Max build team and I are using pieces of wood cut to different lengths.
How high can it go? We can use my head to, no, okay, wait.
It takes a while to get together, but once it's done, it looks just like the kinds of doorways stone buildings had in ancient times.
Ta-da! There you go, a maxed out Corbold arch. We went straight up until we got to these layers, and they got a little bit closer and closer to the middle until the last piece is one big solid piece. And if we built this right, it should be strong enough to hold me up. Yeah! Science! Woo-hoo! Well, it held me up for a minute, didn't it?
We rolled our pasta and constructed one truss. Now we've made a lot more rolls of pasta and connected them all together to make a second truss and a roadway, as well as the cross braces on top. And when we get it all together, we end up with...
Whoa! Pasta bridge!
Pasta bridge!
We did it! We built it. We have no idea how long it will stay up, but it's up. It's doing its bridge thing for now, anyway. I am very excited because, as far as we know, I'm the only one to try to cross a bridge made out of pasta. What do you guys think?
I think I don't want you to be the last person to cross a pasta bridge.
You're absolutely right, but I'm gonna do it. I think we're ready. Yeah?
Yeah.
Okay. Here we go. Oh no! That doesn't bode well for our pasta bridge. What happened here, Kyle?
You put all your weight in the middle of the joist. It snapped.
Uh-huh.
If only there was a way to distribute your weight. Maybe if you crawled?
Do like the military style kind of.
Oh, right, so that I'm putting my weight on more than one spot.
Yeah,
Exactly.
Oh, wait a minute. That gives me an idea. You guys stay right there. I know what to do. I know what to do. I know what to do.
You're coming back, right?
Skis distribute your weight over a large area so you don't sink in the snow. That's what skis do, which is perfect for the pasta bridge.
Come on.
Okay,
Come on.
Carefully.
Uh-huh. Is it working?
It's working.
I hear some cracking.
This might do it.
Uh-huh.
Try to spread your legs apart.
Spreading my
Distribute
legs
your weight.
apart.
Distribute your weight.
Distributing my weight. It's swaying a lot.
Oh, man.
Oh. Whoa. Crossing the pasta bridge. Woo, high fives. There you go. Science Max, experiments at large, pasta bridge, skis. What more could you want? Maybe a pasta chairlift of some sort.